Alright, we're going to kind of start where we kind of left off last time in the synchronous circuit stuff. And we're going to look at fan-in logic. And all combinational logic that fans into flip-flops can be included in the flip-flop inference block. So I'll show you how to do that. So this little blob here represents the combinational logic feeding into the flip-flop. So we can merge this type of stuff into a single flip-flop inference block using the same clock. And then this, of course, is just a combinational output decode that you might have that's separate in case you don't use the direct flip-flop output. So let's look at an example here. Here we've said that we have these 4 inputs and we're going to produce an output. And we've said that the product, or the addition of AB, is called AB, and the addition of C plus D is called CD. So that's what this represents, these two things. And here we've made an always block that has 2 flip-flop inferences in it, because we've used non-blocking assignments with this type of structure, which says that we're going to generate RTL code. And here we've said that the AB flip-flop, that would be this one, equals AB, which is our assignment we made up here. Okay, so this is one method we could do it. And the CD flip-flop is going to clock in the CD addition. Then we've said that ABCD is equal to the addition of the output of those 2 flip-flops, the AB flip-flop and the CD flip-flop. And here we've created another always block that runs on the pause edge of clock using a non-blocking assignment, which is going to infer a flip-flop. And this flop is called the ABCD flip-flop. And that would be this one right here. And that's the addition of those other 2 products from the output of the other flip-flops. Then after this final flip-flop, we've said that we want to create a mux, and it's going to select a particular bit based upon the input called S right here. So this is one way you could write that particular structure that you want. Okay, now let's look at another way. So like I said previously, let's go back, that you can merge into a single flip-flop inference block this combinational logic and the flip-flops. So let's go look how we could do that, how we could do this. You can just put it directly in here. You could say the AB flip-flop is equal to A plus B and the CD flip-flop is C plus D. So that infers this whole thing here, or this whole piece here. And then for this flip-flop and this logic, you can combine that all into a single statement. So here we have 2 always blocks with non-blocking assignments, which says that we're going to create flip-flops. And then the final output, we've just made our selection. Any questions at this point? How come I didn't stick this back behind this flip-flop? That's my question for you. Could I have done that? Yes, you could put it back here if it didn't make a difference in timing. It could be that when this clocks at this flip-flop here, it may be that S isn't to the value that you want yet. And so it may be a timing type thing where S is not valid until this clock edge, and so you can't make this decision until then. So
isn't there a timing thing with the 2 different clocks?
Say that again?
You've got the three flip-flops, and some of them change state at the same time the other one is sampling.
Yeah, well, let me give you an idea what you might, let's see if I can. Let's go to a drawing thing here. Let's say here's the one stage of the flip-flop. There's another one. Pretty little waveforms I draw, I know. Okay, let's say we have our A, B, and C, D, and let's say that, you know, they're valid. They change somewhere in here. Okay, and okay, so if we're clocking, this is our clock. Then this stage right here, I'm sorry, I said this was AB, so we're assuming we've already done that first addition stage. There's AB, and where's our picture here? What was I doing? So this is the ABFF. Let me just redraw this here. ABFF, and then we have some addition stuff here. Sorry about that, not too good. And we're going to do that with the other one, and then that goes into this flip-flop, and same clock. Then we have the output of this, and that was, I think, what we call that, ABCD. I cannot draw with this thing. ABCD. So then we would have ABCD, and that would occur here. Okay, see if I did that right. Yeah, there we go. Okay, then we've got this other thing, S. So let's go back. There's S. There's O. So it could be that, you know, our S, and the reason maybe we had these flip-flops, this is just an example, maybe S, you know, maybe it's not valid until this time. Okay, so maybe it's not valid, and we knew that this was going to change here, so we know that the sum is going to occur on this clock, and so we aligned our S.
There was kind of like a race condition.
No, this is
the output of the first flip-flop and the input of the second. That well, one's transferring, the other one is looking at the output of that AND gate in the middle, which I assume is very fast relative to the clock.
Oh, okay. You're talking about this path right here.
Yeah, I'm thinking that the output of the second flip-flop is maybe. You don't know whether it's got the stuff from the same clock cycle at the input flip-flops propagating all the way through at the same time, or if it takes another clock cycle for it to get there.
Yeah, that's actually a good question. We're going to deal with that in the lecture today, but what will happen is your timing analysis tools, and we'll talk about that today, they will actually keep track of whether or not you can meet the timing between this clock and the next clock with all your logic that you have. Okay, so here's what happens. On a clock edge, let's pick this one right here. You're going to have a clock to Q delay. Okay, there's going to be some amount of time that it takes from the clock edge rising till the data actually comes out. That's why I've shown a slight delay here in the AB flip-flop. Okay, does that make sense so far?
Absolutely.
Okay. So then you have not only the delay from clock to Q, but you've also got the delay of the wires, you know, and you've got the delay of the actual logic, whatever it happens to be here. And then you may have some more wire delay, and then you actually have what's called a setup time. and that is the data has to be valid here on this D input a given amount of time before the clock goes high. Okay, so based upon whatever your cycle time is, let's say this was 10 nanoseconds from rising edge to rising edge. Okay, and this clock to Q was 1 nanosecond. The wire plus all the logic delays was, say, another 6 nanoseconds, and you had a setup of 2 nanoseconds. Would it meet it? Well, the nice thing is you're not going to have to keep track of all that as long as you're using sequential logic that's clocked and the flip-flops are using the same clock, because the tools will actually do that for you. And if you meet timing analysis, and that's very important that you always meet your timing analysis so that you can guarantee that this thing will always work in this manner like we've done here. This is what we want to do. So we'll talk about that a little bit more during the lecture. Okay, shall I continue on, or is there another question? So this actual O here, you know, it's going to be delayed sometime from whatever S and the delay we might have here coming out of the flip-flop and whatever this selection logic is. So maybe O is, you know, somewhere over here. It changes. You know, it might be out here somewhere. Okay. Now let me go back. Now, before we made two blocks, since these flip-flops are all under the same control, run on the same positive edge of clock, they can all be put within the same always block if you like. So it could just reduce down to something as simple as this. So the AB flip-flops are equal to A plus B, and the CD flip-flops are C plus D, and then the ABCD flip-flops are the addition of the other two. So this right here, along with this, would describe this whole circuit here. When you're using case statements in your RTL code, they don't have to be full case statements that we talked about, and they're only required to be full if you want to avoid latch inference. Okay, most of the time you do want to avoid latch inference. And in this case, this would be a priority encoder method since they're not parallel. Also, blocking assignments can be used to compute intermediate results. So here I've said that AB equals A plus B, and this is a blocking assignment, whereas these are non-blocking. Okay, so this is this statement right here will not infer a flip-flop. So you can do that in your code. So in lab 10.1, you're going to learn how to infer resettable flip-flops with fan-in logic. And in lab 10.2, you're going to learn how to allocate fan-in and decode logic in various always blocks. So let's talk about state machines now. And with state machines, you want to split your state machines into basically two blocks, a combinational only and a flip-flop only block. So that's what's represented here. Okay, and the input of the flip-flops is a function of various inputs plus typically feedback through logic, combinational logic. So here's a simple finite state machine example. Here we have 4 states, and we said that if we have some input that's a 0, we stay in this state. Otherwise, if we have a logic 1 for signal, then we go to this state. When we're in this state, if we have a logic 0 on some signal, then we go back to this state. Otherwise, if we have a 1, we go to this state, and so on. So this would represent a state machine. So the best way to start creating this state machine is we start off and we create names for our states. And we do that using parameters to define these states. So in this case, we need 4 states. So in order to have 4 states, we're going to have a register that's 2 bits wide, something that can contain a value, 4 different values. Doesn't matter what those values are, it just you need to be able to contain that many different values. So here we've said that our outsync state is 0, and typically you want to make your reset state 0, 0, 0, however, all the flip-flop bits are 0. And the reason is typically your FPGA, if you're designing an FPGA, those flip-flops are going to come up in reset state automatically. But it is something you need to be aware of, you know, what state you come up into and whether or not you need to force it to a particular state, like use a reset signal and force your flip-flop to a state. But I typically create my state machines so that the reset state is always the 0, 0 state. So here I've said that my outsync state is 0, my syncing state is 1, my in-sync state is 2, and my sync loss state, is 3, and my sync loss state is 2. So then you declare, typically you want to declare 2 registers for your state register and your next state. So here I've said that my current state, I'll call it state FF. It's a register that's 2 bits wide. And I've also declared that my next state is a 2-bit wide register, because you're going to use both of these in your design of the state machine. And you can call these whatever you like. Okay, any questions so far? Okay. Now, the next thing we need to do is we need to describe this next state or the output decoder using a combinational always block. Okay, so notice here we have an always block, and we're using blocking assignments in here. Okay, and we want to make sure that we define every condition for next state. So you see next state all through here. Okay, we don't want to leave any of those undefined, or what happens? We could wind up inferring a latch. Okay, and then the other clue here is we put in a sensitivity list. So in this sensitivity list, we only need these 2 things. A thing called frame, which is our input, our test condition, and our flip-flop state. So those are the things that we use in here. So we start off, and one way you can do this to be sure that you define all the cases for next state is just at the very beginning you could just say that next state equals state FF. Okay, and then if there's any changes you can cover that in your case. Another way to do it is, instead of putting this here, you could put in a default case statement and define it there, and I prefer to kind of do it that way. So then we have a case statement. This is a good way to do this. So you say case and then your state flip-flop, and then you start defining the different states and what it's going to do, so that if I'm in this state, outsync, and if frame signal comes along as true, set to a 1, then I want next state to be able to be set to syncing. Okay. Similar for these other states, I define what next state is. So here we have next state, which is combinational logic. The output of this, called next state, is a function of our current state and any input signals that we wish to use. And then this next state, of course, will be fed back to the input of the flip-flops. So now let's see how we connect that. Okay, so now you're going to make another always block, and you're going to say always at pos edge or neg edge of clock. okay, and you're going to use these blocking assignments. Wait a minute, I lost my mouse cursor here. Okay, so here we've got non-blocking assignments. So this is going to be turned into RTL code that produces flip-flops. And here we've said that we want a synchronous reset by putting this if statement in here. So if the reset is true, we're going to set the state to outsync on reset. Otherwise, it's going to use what we've defined in our combinational logic for the next state. So that's how it will advance to the next state on the next clock. If there is no output decoder, or the outputs are all registered, the next state decoder can be included in the sequential block. So here's another example where we have actually included the whole thing in this block, because it's a fairly simple one. And we're using the, well, according to this. So this is another method that you can use. So in Lab 10.3, you're going to learn how to model a finite state machine. And there's directories in there that'll have code in there for you to play with. So that's basically how you create your state machine. We'll look at some more examples of that in after the class. So now we're going to talk about clock domain crossing briefly. Let's say that you have more than one clock. Let's say you have some flip-flops that use CK1, this clock. Then you have another group of flip-flops that are running and they're doing stuff on a different clock. So how do you handle that? Well, first of all, let's just say a module can contain more than one clock. Okay, so here in this example I have two always blocks, two different clocks. And here I've said on clock 1, this S flip-flop, which would be this one, is equal to the input. And then this other Q2 flip-flop is basically equal to the Q1 flip-flop, and the Q1 flip-flop is equal to the S flip-flop. So this is what we have right here. So if you're going to create multiple clocks, you're going to have to use different always blocks. You can't use the same always blocks. You've got to separate them like this. Be sure to do that. Now the reason that if you're taking data from one clock domain into a different clock domain, you can't do it directly. There's different methods you can use. This is one method. Let's assume that this clock here is running at, say, 10 megahertz. And this one over here is running at 20 megahertz. It's faster. Then this would be an acceptable method so that we don't have metastability issues. What happens is if you only have one flip-flop here and you go from this clock domain into this clock domain with just one flip-flop, you're going to have metastability issues and you're going to have failures in your logic. So if you double buffer it, that's what this is called, double buffering, then instead of maybe it failing every tenth of a second, then maybe it only fails once every 100 years now. So it's a big improvement. And you can, if you're not familiar with metastability, we could talk about that later. Another method from going from one clock domain into another clock domain is to use a FIFO. So one side of the FIFO clocks in using one clock, and then the output side uses a different clock. And typically these type of FIFOs have the logic built in so that there's not metastability issues. Some guidelines is try to use a single clock domain per module, but that's not absolute. So if you don't, one of the better things to do is to put a prefix on signal names so that you know which domain it's in. So let's say you had one domain that was running on a signal called sysclock. You might want to put sys underscore on your variables that are running in that domain, especially if this is all in one module. And then let's say your other domain was, oh, I don't know. Anyway, you put some other prefix on those variables for the second clock domain. So it's important, very important, that when you cross clock domain boundaries that you do it very cleanly. And so a couple of methods are FIFO or double synchronization flip-flops. Now, of course, if you're going from a fast domain into a very slow domain or a slower domain, then you might not be able to do the double flip-flop. You may have to do something different, because maybe, let's say in the fast domain you're running at 10 megahertz, and in the slow domain we're running at 1 megahertz. But let's say that the signal that we're trying to capture out of the fast domain is only 1 clock wide. Well, then the slow domain may never capture that. So you're going to have to use a little different technique, but still do your double buffering type thing. So anyway, these are a couple of the methods. So in Lab 10.4, you're going to learn a little bit how to deal with these multiple clock domains. So let's talk about synthesis constraints. And synthesis constraints, we talked about a little bit in the past here, are used to improve timing performance. So maybe things like minimum area or best speed, those are usually some type of implicit constraint. So typically you're going to feed your RTL code plus your constraints, and those are your design inputs. And with some sort of constraints versus no constraints, you should see some sort of improvement in your timing analysis. And however, it may take a little longer to compile once you put certain types of restraints on your logic. And sometimes, you may not be able to meet some timing, you may not be able to meet your timing analysis, and in that case you may have to actually go into changing the way your RTL code is written. You may have to modify it. So there's a lot of trade-offs that you can make in your design. So the specification mechanism to put these input constraints in are tool specific. Some of them have graphical interface where you fill in templates, such as if you're using Alteryx's Quartus tool. It has some things that you can check and tell it, what kind of constraints you want. If you look in the documentation, usually you can find some command line type constraints or script type inputs. Or you may be able to actually embed directives in comment lines right in your HDL source code. So these are the typical methods that you would have. I'm not as probably firm on this guideline as I used to be. It's pretty much the way you want to do it. So let's remember that our gate delays come from the target library, and the clock frequency is design specific. So we have to be able to describe that clock to our tool. It needs to know things about it, such as frequency, the duty cycle, whether or not it needs to use a global clock net, say in the FPGA, because a lot of FPGAs have dedicated routing resources just for clocks. So you're going to need, at some point, you're going to need to specify some information, in your tool as to information about the clocks that you're using. Okay, so here we have this, we'll just say this clock is 10 nanoseconds. That's something that the tool is going to need. And then when it has all of this information, then like I said, it's going to be able to calculate whether it's going to be able to meet timing from one clock to the next, whether the clock to queue plus all the delays of the logic plus the input setup time that is going to be met. Okay, you may even have clock delays too, but the tool will calculate all of that for you, so long as your flip-flops are running on the same clock here. And all of this type of information comes from the vendor's library for the particular FPGA part that you may be using. So it does all this type of work for you. Okay. However, you have to be careful, since a lot of the tools can't handle clock generation circuits. What do we mean by that? Such as this, like here I have an example of a clock divider. So I've run this clock, it's running on this flop, I've run it into this one, and I've done a divide by 2 function with this flip-flop, and then I use it as this clock over here. Okay, it can no longer then give you a accurate timing analysis for things that you do like this, because these aren't running on the same flip-flop. So you're going to have to, well, I take that back. You're going to have to see if your tool can do it or not, and you're going to have to learn how to specify whether the what the tool might need in order to be able to do those type of calculations. So this is something you need to be aware of. Some tools can handle clock inversion, okay. Some tools can compute propagated clocks. Most tools can model the effect of distribution, such as delay and skew. So here we have a clock. Ideally it rises at 0, falls at 5, and goes up at 10, but maybe due to rise times it's delayed by 2 nanoseconds, and fall times maybe it's delayed by 1, so you get something that looks like this. So that would be a delayed clock. It can handle that information, and it can make the necessary calculations also for skewed clocks. Another thing that you're going to have to specify, since the tool can calculate from flip-flop to flip-flop using the same clock, then we run into the case where, okay, inputs. What about inputs? So the synthesis tools have no knowledge of the external environment on the data inputs. Okay, they don't know the things like maybe the strength of the driving device. They may not know the data arrival time. And a lot of times the tools will usually assume infinite drive by default. So here we have external logic. It's being driven by this clock, and so is this internal logic. However, in order to calculate everything from this clock to this clock, it doesn't have a lot of this information like clock to Q, and then the delay of this external logic you have. And so it's going to need to know some information here so that it can meet your timing analysis about your inputs. Okay, because you may have some more logic in here before it gets to the flip-flop. Similar for output. Okay, it doesn't have any knowledge of the external environment on the data output, so you're going to have to give it some type of information, such as the load of the driven device, the number of driven devices, data required time, all of those type of things. Sort of a guideline here for allocating time budgets to input and output paths is maybe give your let's say you have a clock period of 10 nanoseconds. Let's say you dedicate 20% of that to any logic that might come after the flip-flop, and maybe you dedicate 60% for off-chip. Okay, and then there's 20% left over for routing. There's also things called false paths. Okay, like in this case here for this example, here I have a two unrelated clocks. Okay, and maybe I have to do this. Maybe there's a real reason, and there's logic in between. However, we don't want it to give us a warning or some failure that we're not meeting timing analysis. So typically most tools will have some sort of input to declare that there's a false path. So we can tell it, okay, from this Q to this D, ignore the timing. And it's our responsibility to make sure we've done things like make sure there's no metastability issues, that we've properly clocked it from one clock domain into the other, in which case there may be more flip-flops here. But then it's our responsibility, okay? And we don't so much care about the actual delay time here because we're going from one domain into the other. So the timing analysis is performed by tracing delays through the combinational paths. Okay, so you don't have to do any simulation to do this. It doesn't have to feed any stimulus in order for it to figure this out. It calculates it, okay, and what we previously talked about, the delay calculator. So the tool will actually trace all the paths, even those that may not be exercised under normal conditions. So let's go back to our example here. where we have a clock to Q delay of, say, 4 nanoseconds, and then something here that causes a delay of 3, another thing that causes a delay of 3, and then a setup time, which would be the D input, has to be valid at least 2 nanoseconds here before the clock edge rises. So, and another condition here, we've said that there actually happens to be a delay on this clock path. And our basic clock period is 10 nanoseconds. So let's see what happens here. So for data input, that's to get to this point right here. We start off here. So then we have a clock to Q delay of 4. Then we have a delay of 3, so that puts us at 7. Then we have another delay of 3, and that puts us at 10. So that's where we're sitting for this D input. And then for the clock itself, the clock input, we're going from one clock to the next, so that's 10 plus the delay, so that's 11. So the slack time, what we call the slack time, is actually the 11 minus the setup time minus the clock period here. So that gives us a -1, which that says that we did not meet our timing analysis. And the reason is that basically D is only set up 1 nanosecond before the clock rises, so that's a setup violation. It has to be there too in this case. But your tools will calculate that for you, since you're doing synchronous circuits using the same clock. They'll make all of those calculations for you and tell you that you've got these violations, and then you need to go fix it, or else you're not going to be guaranteed that it'll work under all conditions. See, there's other factors that also influence this, such as temperature that the part's running out, the voltage the part's running out, or process variations where it came off the assembly line. So all of these things the tools will have information about, and so they'll do all these calculations, including temperature, voltage, and process variations normally. Okay, but the key is it needs to be a synchronous circuit where you're using the same clock here. Okay, so now let's say these flip-flops are in this clock domain. You have another set of flip-flops in another domain. It can take care of all the domains. Okay, so all we're talking about is from clock to clock within a domain. And these are some other factors that can affect timing too. Output net lists. They don't have to be in the same language as the RTL input. It could be in VHDL or Verilog or another format. And most tools can flatten the hierarchy. So in Lab 10.5, I want you to become familiar with setting constraints and see how constraints affect the synthesis outcome, and witness how operating conditions affect timing estimates, and examine some timing reports. Some of the topics I haven't covered in this class so far are user-defined primitives, switch primitives, the specify block, and a programming language interface, PLI, so where you can build your own system tasks if you like, and predefined system tasks, which are specific to each simulator. I also haven't discussed some of the newer Verilog 2001 things, such as say the generate statements. We'll take a look at that right after this lecture. A lot of these things you need to, I've kind of just gotten you started good in it now. You should be able to actually do a lot of design with what we've talked about. It's just going to be a matter of practicing and getting used to it, maybe looking at examples, and maybe we have some future things where we get together here now and we start going through some code. But you go take a look at your book, if you've got a Verilog book, and you'll see some things that we haven't necessarily discussed yet. But you should have more than the basics at this point. These are some books that I like. This book right here, this bottom one, I have this in a hardback. It's pretty good. There's a lot of different books out there, so it's up to you which book you want. So I'd like to say thank you for attending, and that's all of the lecture for today. Any questions? Can anybody still hear me?
Oh, yes.
All right, let's go back. Oh. So one of the things I've been doing recently is I've been designing this new module called in-wire transmit and in-wire receive. They're very similar to the one-wire stuff that we looked at, but they're a little more robust. Questions? Guess not. Okay. Let's take a look here. So would you be interested in maybe looking at this in-wire stuff that I've created? Because right now I have the my new Mercury code and the new Aussie Janus FPGAs are and Penelope, I'm working on that one right now, are all based on this new in-wire stuff for doing communication between FPGAs now across the bus.
I certainly would. This is Al.
Okay. So let's look at the transmitter. Very similar to what we had in the one wire, except it got simplified just a little bit. So I'm still using my data bits for logic 0 and logic 1 that look like this. And for the actual data output signal, the one wire signal itself, the data out has a after power up reset, there's a delay time, followed by however many data bits, like this, that you specify, followed by a number of low bits. And that period from here to here is the send frequency. Okay, so once it sends the data bits and then the low bits, if you want to repeat it, you can. If you don't, you don't have to. It can be just a one-time deal that it sends it out in this particular one. Before in the one wire I repeated it over and over, but you don't have to. So you'll notice that in the one wire I had, before I sent out the data bits, I did some sync bits. I no longer do that. It's just pure data bits plus this low time. The receiver now is smart enough that it doesn't need the sync bits. It will actually figure out its timing right out of the data bits. So basically in the states there's a delay time here, and then here's what the actual data bit may look like. The first quarter it'll be high. The second and third quarter it will be whatever the value of the data bit is that we want to send out. It could be a high or a low here. And then in the fourth quarter it's always low. Then I also have some handshaking signals in this new design, and I call them X-ready, X-request, and acknowledge. So when the data is ready, the ready signal will actually go high, and then if you come along with a request while the ready is high, then it'll send back an acknowledge, and then it'll actually clear the acknowledge when it gets partway through the very first data bit. That's what's represented here. Now in this design I'm assuming that the user may use 2 clock domains. So you'll notice here that I have a signal called I reset and one called I clock, and another one called X reset, another one called X clock, along with some other signals here like data, request, ready, and act are all in the X. So in this case I put an X specifying that all of these signals are in the same domain, and these ones starting with an I, they're in the same clock domain. So let's say that my I clock domain, this is a default value which you can override since it's a parameterized module. I'll just say the default frequency is 144 megahertz. Okay, because in one of my cases inside the let's see, which FPGA is that? That's in the Aussie FPGA. I actually take the 48 megahertz IF clock and I use an Altera mega function and I multiply it by 3 so that I get 144 megahertz. Now this is just default values. I just did that while I'm working on it, just kind of keep things straight in my head. But you can override them, like I said, because in other modules I use this, but I set these equal to the same frequency. I use the same clock. But in the Aussie FPGA, I actually use 2 different clocks. So I'm making this module, as we go on you'll see, I'm making this module where you could use the same clocks or you could use different clocks. And I'll show you how I do that. So here I've said that all of these signals starting with the X are basically running at this X clock frequency. And the ones starting with I are running at the I clock frequency. Okay, so now, and then of course I have my normal definitions, calculations based on the parameters. Now I want to show you, and then here's the state machine, this local param I've defined for my states. And I'm going to show you something new here. See this generate? There's a generate statement, and the end of it here is the end generate. Okay, this is new for the Verilog 2001 standard. And the nice thing about this generate is you can use it to define whether or not you're going to instantiate certain blocks of logic in your code. Okay, so I said that if these 2 clocks, this I clock frequency is equal to the X clock frequency, then all I'm going to instantiate is just these assign statements. Okay, so let's go back up here. Remember our parameters here, X clock's frequency and I clock frequency. So if they've been defined as the same, let's say that they were both going to run in, let's say we're putting this module in Mercury, and in Mercury I do set them the same. Let's see if let me pull up some here. I think I have my new code available. Okay, so here's an example. Let me find the transmitter one. Here we go. Here's the transmitter. Now this in-wire transmitter I've instantiated. Here's its name, MDIQ. It's going to send out the data that comes from the receiver portion of Mercury. Okay, the I and Q data. So here we are. Here's the data, RXI and RXQ. Okay, and in Mercury, and this is working right now, here's the receiver block instantiation. Okay, does all the DSP code for the filtering and all that stuff. So the outputs are these RXI and RXQ here. And this stuff is running at the 122.88 megahertz. So that's one of the parameters I feed in for the data, and I send a request based upon this variable here, and this variable is running at whatever our data rate is. So I get a pulse every so often. Notice since it's a parameterized module, I'm overriding parameters with this part of the instantiation. So like, here's the send frequency of the transmit data, 192 kilohertz. Okay, That doesn't mean that this LR fall is running at 192. This is just how fast out I'm sending my one wire data. Okay, so this could be 48 kilohertz, 96 kilohertz, or 192 as to how often I send this data out. I request it to be sent out. This is the actual data bit rate that it's going out across the one wire signal. So it's a separate thing. Okay, in this case I said that the send frequency is 192 kilohertz, and the data bits, there's 48 data bits that I want to transmit. That's this data right here, adds up to 48 bits, 24 for I and 24 for Q. The I clock frequency is 122.8, and so is the X clock frequency. Okay, and here I have the I reset is this, and the I clock is this, and then I repeat it for the X reset and the X clock. I'm using the same clock in here. So now we go back, and so I said if this is the simple case. The simple case for this is if both the clocks are the same, then I can assign my signal called X ready, and the X ready is the actual signal pin here. Okay, it's running, since it's running at the same frequency, I'm just doing an assignment from my I ready, which is down internal down in here. And I ready is running off of the I clock. Okay, my generation of I ready. So I'm not crossing domains, so I can simply assign one to the other. And that's basically what I've done for these handshaking signals, such as I ready, IAC, data. I can directly assign the X data that's coming in, because X data is an input right here, right there. It's an input into this module. So I can assign the X data to my internal I data. So it makes it very simple for this case where the clocks are the same. However, if the clocks are different, I want to instantiate some double buffering. And then that's what this part of the else is doing here. So it will actually put this code in when they're the same. It'll put this code in when they're not the same. Okay, and you can see this. These are the here's an always block. This one's running on X clock, and this one's running on I clock. And so I'm going from one domain to another. In this case, I'm taking the I ready to an equivalent X ready in a different domain. So this is just a double buffer. Remember the double buffering? That's all this is doing. So this is see, I ready gets clocked into XR0, XR0 gets clocked into XR1 flip-flop. Does that make sense, or you want me to draw it out? Let's I'm sorry, I didn't need to do that. Big eraser. That's not a big eraser. Wow. Okay. Okay, so here we have I ready. So here we have iReady, which is in the iClock domain, and since I've specified they're different clocks, I want to then take it from the iClock domain to the XClock domain, and so that's where the double buffer comes in. So this concatenation operator, as you can see, the iReady gets clocked into XR0, and then the XR0 bit here gets clocked into XR1. So this is just a short way of writing the notation. You could have written this separately. You know, I could say that XR0 equals iReady, and I could have said that XR1 equals XR0. Okay, now you'll notice I did have this delay, and this TPD is a parameter that I can change. And it's okay to put these into your RTL code. It will ignore them. Okay, they don't actually get synthesized. It's just I use this for simulation purposes only, so you can ignore it for synthesis. So basically this is what I've done for this particular statement. Does that make sense? Oops, let's go back to... So here I've clocked iReady, I've gotten it into my XClock domain because the clocks are different. Here I've taken my internal my iAcknowledge, which is down here, generated down here, and I've put it into the X domain, which is the domain that the user is going to actually be reading signals on the interface at. So the generate statement is very useful for instantiating different blocks, such as always blocks, or registers, wires, assignment statements. So you can make your parameterized module even more versatile this way. And then these, of course, are all the non-blocking assignments for the state machine. And then the actual state machine. So basically all this state machine does, it comes up in idle, waits a certain amount of time in this state until this counter has gotten up to num delay clocks. Then it goes to the wait state, and here it waits for an acknowledge, and then it starts going right into sending the data. And the first part of the data is this Q1. That's where it sends out the logic high for that Q1 period of time. So there's a counter I have that's running, and it gets before it gets, just when it goes to this state, this B count gets set to 0. So then that counter will be counting. So while it's not equal to this Q1, it just stays in this state. So that's how I get my first quarter of the data bit. That period right here. So from here to here is one data bit. So I have parameters that have calculated how long this needs to be based on the frequency that we're sending things out. And same thing for this one and this one. So the actual data bit is this, the logic 0 or 1 actually gets put out right here. And this time is high and this time is low. So then in the state machine, it puts out a high for this Q1, then it'll go to the Q2-3 period, in which case it'll actually put out the actual data, and it'll put out the least significant bit. And then every time that then when I go to the next bit, it gets shifted. I'll show you where it gets shifted if you like. But anyway, it puts out the least significant bit, so it'll either be a 1 or a 0 during this second and third quarter of the logic 0 or 1 bit that we're putting out. Then after it does that, it goes to state data Q4, in which case it always puts out a logic low onto the data out signal, and then it determines whether it's finished and goes to the appropriate state. There's a lot more to it. We just have to. I think we're running out of time here right now. But any questions for today?
I have a few more minutes on
Okay. Does anybody have any questions?
so if you want to keep going, you can go.
What about things that you would like to see discussed for another? Well, it won't be a lecture. It'll just be a time that we can get together and go through some code or whatever you want to discuss.
Well, I'd like to see more. How about on what is left in the lecture? Do we have one more, or was that it?
No, that was it. It's now actually
Okay.
getting in and using it. With what you've been given so far in the lectures, you should be able to create most anything you need to. It's just a matter of learning how to do it and getting used to doing it. You know, looking at examples, looking at real code. Or if there's particular topics.
Walking through the code like this is probably the most useful thing at this point.
Okay. Is there something specific you'd like to see? One of the things I'd like to talk about a little bit is a little more on this in-wire is the actual receiver and how it no longer needs the sync bits, and maybe my method of, you know, how I came up with it, maybe even. The transmit.
That sounds good.
Yeah, the transmitter itself is fairly straightforward. It's just a matter of, you know, coding it according to, you know, I've defined that I want it to be so many data bits that go out and so many low bits, and that defines my send frequency. And of course all my calculations here are based on that. And then it's fairly straightforward, other than the generate stuff here was new. You know, going from one clock domain to another so that I don't have metastability issues. We could define, I mean, we could go through more of this, each one of these in detail if you like, or we could just go on to the receiver and how it no longer needs the sync bits. It just derives off the data bits, what I did to do that. Or we can do both.
Well, the latter, I guess.
Receiver, okay.
Yeah, the receiver.
Okay. And I guess I could post these now that they're working. I could probably post these up on the website.
Can we go through some of the Mercury code too, like the decimation filter maybe?
Okay, we might could do that at some point. Those, though, as far as the decimation filters, they're pretty just straightforward if you look at the code, unless you have a question on how it's implemented. I mean, they're just, you know, they're decimation filters. I don't know.
Okay, I haven't looked at the codes, so just something I was interested in.
You know, I have here's actually a simulation of the in-wire stuff, where you can see the actual data going out. You know, you might want to try simulating some of this when I put the code up. Is create a little test bench that instantiates the in-wire transmitter and that instantiates the in-wire receiver, and then actually get them to do this. I could give you the code if you want to, but it'd be good if you could actually learn how to do that. Get it to transmit and receive the data by instantiating them. So one of the neat things about the receiver is keep in mind, let's say that you have a transmitter on Aussie and it's sending some data over to Mercury. You know, like maybe it's sending frequency, what we call the command and control data. That all goes across one of these in-wire things now. So Aussie transmits using the in-wire transmit, and then Mercury receives it with an in-wire receive module. But now when I'm debugging, let's say that my system's up and it's running and I make a change in my code for the receiver. Okay, so I hook up my byte blaster to Mercury and I program it right on the spot. Now I haven't reset Aussie, but when you reprogram Mercury, it gets reset. So here I'm transmitting along, okay, and when, let's say this is coming out of Aussie, and all of a sudden, you know, I reprogram Mercury, and let's say it starts in the middle of this data stream. Okay, so the receiver needs to be able to basically recover no matter where you hit this data stream. So that's one of the requirements I had in the design. And I actually, how much time do we have left?
It's 5, but I'm good for another 10 minutes or 15 minutes.
Well, let me show you one thing real quick. And I made this, let's see if I still got it in here. Commented all this out. Okay. Let me comment this line out so that I reset. Here I'm resetting both Aussie and Mercury basically at the same time. Now in this case, I'm going to reset Mercury. I'm going to finish it much later so that it starts basically out in the middle of the stream. Okay, so right here in this simulation, you see that the receiver kind of starts off, and this thing called pass in the receiver is what determines that it has figured out how to sync to the data, and so all these 4 bits go high. But it started off running at the same time this one did, so it didn't have any trouble. It could figure it out real quick, so that on the second data stream it could grab the data and knew enough about the width of all these bits in order to grab the data properly, and sure enough it did, the 35C that I sent out from up here. So it only took it one stream to get it. So now if I resimulate where we throw it into the middle, oh, wrong one, sorry. Oh, I didn't save it. Did I? Yeah, I did. Okay, let's see if I got it. No, I didn't save it. What did I do? Save. There we go. Now, let me recompile. Okay. Now you can see what happens is Mercury, and that's, I know it started right here because this is where it first starts generating some signals right here on this signal called dB rise. Let me zoom in. So here the receiver started, but you notice it's trying to figure things out, and all of a sudden it got a long space in between because of where it started. But it's actually able to figure it out, and finally gets to a point that says, aha, I've got it figured out. So all of these pass bits are going high. And then on the next, not on this second cycle, but on the actual third one, by the third one it's got it figured out and it's latched the data in now. So it's working properly at this point. So that was one of my main requirements in eliminating the sync bits. I had to still figure it out and make sure that no matter where I hit this data stream after, you know, say Mercury comes up, or I reprogram it, because I didn't want to have to reload or actually reprogram the FPG. I just want to be able to download it through the byte blaster because it's much quicker that way while I'm debugging. So, and this works. So there I hit it toward the end of this stream where it had to go across this long space of time, and it thought, no, I've got differences here, it's still not correct, the differences in the bit widths. So then it went through the process again, and I'll show you how that works sometime. So anyway, it'd be good if you could actually instantiate these two modules, learn how to drive signals going to them, and then see if you can get a simulation that looks like this. And let me do this. I'll give you the instantiations here on the screen so that you can see them. Okay, so you can do the same thing that I did. Here are the two instantiations. So if you'll do this and then figure out what you need in order to drive a clock, you should know how to create a clock running at a certain frequency. And you should be able to create a simple reset. Let's go, I'll give you some of that. So like, here we go. So you can see that in this, I commented a lot of stuff out here right now, so ignore all the comment stuff. Here's an initial block, and then in the beginning of the initial block I've set my reset high, or resets. I've got two different ones. I did this one for Aussie, for the transmitter, and this one for the receiver. So I set them both high at the same time, and then I delay some time, and then I set one of them low, and then the other one I schedule it to go low a certain amount of time later. Okay, and then as far as signals to drive, you're going to have to drive some request signals, look at some acknowledge signals. So that's what this type of code right here is doing. And did that for, I created like three sets of data, just looking at the requests and acknowledges. And then at some point I stop it. And see if you can recreate that and get a similar type simulation. And then change the when the reset finishes for the receiver versus the transmitter. And that'll give you some good practice. So I think that's it for today. Unless anybody has any more questions or comments.
Well, Kirk, thank you very much. So we're still going to plan on meeting on Thursday?
We can do that if everybody wants to.
Yeah.
Send me emails for suggestions for
Okay,
Thursday.
see everybody Thursday then.
Okay. Yeah. If everybody wants to send me an email as to their suggestion of what they'd specifically like to see, that way I'll remember.
Okay, thanks. Bye, everybody.